Okay, good morning, everyone. Okay, thank you for joining us today. My name is Chung Park from SK Telecom in South Korea. And along with my colleagues, Taesan Kim and Hyungjun Yoon, and we are very excited to present our research paper, The Pacer and Runner Cooperative Learning Framework Between Single and Cross-Domain Sequential Recommendation. Actually, we and our team have developed this series of sequential recommendation systems based on the various types of data sets, such as shopping purchase or geolocation data set or POI data and so on. So our current focus is on cross-domain recommendations, which utilize these various types of data sets simultaneously. Okay, so our research has been applied in real-world applications and contributing to increase the revenue for our company, SK Telecom. Okay, so let's start with the introduction. In the field of the recommendation system, there are two main approaches. The first one is single domain sequential recommendation, and second one is cross-domain sequential recommendation. Okay, the SDSR, single domain sequential recommendation, relies on the historical interactions within a specific domain, such as book domain, while CDSR utilizes the information from multiple domains, such as clothing or book, sports domain, and so on, to enhance recommendation performance. Okay, so we can see that the difference between CDSR and SDSR tasks for each domain is whether or not they use information from other domains in addition to the specific domain. However, CDSR can sometimes suffer from the negative transfer, which occurs when knowledge transfer between domains is ineffective or detrimental. Okay, so negative transfer happens where there are lack of the relation between domains or when there are different level of data sparsity. Okay, so for example, as shown in this figure, the performance of the SDSR based on book domain is higher than that of the CDSR approaches based on the book plus clothing or book plus sports. So this can lead to CDSR approach underperforming compared to SDSR in certain domains. So our goal is to address this issue and improve the overall performance of the CDSR. So of course, there are cases where CDSR outperforms the SDSR. So for example, toy, sports, video, and so on. In these domains, the CDSR outperforms the SDSR. So that's why we start thinking about how we do both SDSR and CDSR tasks in the one model at the same time, and create some kind of the synergy between them. Therefore, we devised a model that performs these SDSR and CDSR tasks simultaneously within one model, but trains the model to cooperate with each other to improve overall performance. So in other words, CDSR is the runner in marathon, and SDSR is the pacemaker, like this. So two persons run together, the pacer helps the runner improve his marathon records. So let's take a look how the model is constructed in detail. So first, let's start with the input data. Let's say we have cross-domain sequence X that mixes all domain information, like this, as shown in this figure, and splitting this X into each domain produces a single domain sequence XA, XB, and XD, like this. So given the cross-domain sequence X and multiple single domain sequence XD, as I mentioned above, we will call the difference between the performance on domain D using the XD and the performance loss or performance of domain D using the cross-domain sequence X. The difference between these two values is called as negative transfer gap. So I will tell you later how this value is used in our model. Okay, in the end, the problem we are trying to solve is the CDSR task, which is shown in this figure. So based on the user's historical behavior, which is a mix of information from multiple domains, we predict what their next action or next purchase, next behavior will be. So let's take a look at the model in high level. Suppose that we have 3 domains, A, B, C, and this is cross-domain sequence. Okay, so if we put the single domain sequence, this single domain sequence of each domain into the transformer-based encoder and pass it through the prediction layer, then we get the representation vector for each item row, like this. Okay, so then SDSR task predicting the next behavior is performed for each domain, and sequence recommendation loss is obtained like this for each domain. Then let's look at the CDSR task. The CDSR task takes the cross-domain sequence of all 3 domains like this as input and run it through the transform-based encoder, this one, and to predict the next action. So note that the encoder, this encoder, is shared by the SDSR and CDSR tasks. So this encoder actually the variation of the MMOA architecture that we will talk about later. So then we can get the loss of the CDSR task based on this cross-domain sequence. So once we have domain-specific losses in SDSR and CDSR tasks, respectively, we can get the difference between them. The difference of the loss between CDSR and SDSR tasks, which is a negative transfer gap. So until now, I explained the way to implement SDSR and CDSR task in one model. So using this, we propose two methods to perform both SDSR and CDSR tasks simultaneously and synergize with each other. The first thing is loss correction with negative transfer gap, this part. And second thing is single cross mutual information maximization, this part. Okay, so first, let's take a look at this first part, loss correction with negative transfer gap. Okay, so as shown in this figure, if we have 3 domains, we perform 3 SDSR tasks and 1 CDSR task. So looking at this more detail, we first find the loss on SDSR task like this, and in the CDSR tasks, we get the corresponding loss for each domain as shown in this figure. Then we then compute the pairwise difference between these 2 losses, pairwise losses difference, and average this difference over each domain. So then these values, the average things is this gamma A, gamma B, gamma C. This is a negative transfer gap, and this yields a negative transfer gap for each domain, and we feed into the softmax functions to normalize the negative transfer values for each domain. So for example, we can see that the relative or normalized negative transfer gap of the domain A is 0.1, and domain B is 0.6, and domain 3 is 0.3. So which sum to 1. Then each of these negative transfer gap is then multiplied by the loss from the original CDSR tasks on the domain-by-domain basis to get the final loss. So these losses is multiplied by this weight factor. Okay. So this process should result in smaller gradients for domains with large negative transfer gap, so reducing the effect of negative transfer. So we will see if this is true in later experiments. Okay, so I mentioned earlier that this encoder is actually the variant of MMOA. So let's take about in more detail. Okay. Okay. So now when we get the losses from SDSR and CDSR, so we use the MMOA architecture of transformer experts, which means that each task selects the best expert set to improve the recommendation performance. So however, since these experts are shared by both SDSR and CDSR tasks, the loss of SDSR and CDSR are somewhat influenced each other. So we wanted to make their losses independent, as if they are obtained from completely different and independent model, so that the difference between them, the difference of each task's loss, the negative transfer gap would be more accurate. So we designed a module called a asymmetric cooperative network with a mixture of sequential experts. So in this module, both SDSR and CDSR performed forward passes for all experts, but backward passes are performed only for predetermined number of experts. So in the single domain sequence, as shown in this figure, forward pass are performed for all K experts, but back propagation updates is performed only for predetermined experts, number of experts. So expert 1 to expert J are in stop gradient. So this stop gradient operation for single domain sequence, and CDSR also adopted the stop gradient operations in expert J plus 1 to expert K. So this stop gradient approach allows SDSR and CDSR to compute losses more independently. So this is a symmetric cooperative network with a mixture of sequential experts. Okay, so let's look at the second module. So single cross mutual information maximization. So this module is sort of regularization method that maximize the mutual information between the representation vector of each item from SDSR and the representation vector from the CDSR, ensuring that two tasks are not trained in two different directions. Okay, for this, the anchor is the cross representation vector of the cross-domain sequence of a specific user, and this positive sample is the representation vector from the single domain sequence of the same user, and negative sample is the representation vector from the single domain sequence of other users in the same batch. So this one and this one put together, and this one pushed together. So let's look at the result of our experiments. So key things we need to see is whether the negative transfer issue has been mitigated in our model, and whether we have seen the performance improvement as a result. So as data for this, we first used the public data set, Amazon data set, and behavior log data set from telecommunication company, so which are real-world industrial data. So each data set contains 5 different domains. So our first research question was whether our model performed better than other SOTA models. So this one is Amazon data set, and this one is telco data set. So actually we ran large scale of data set, experiment with about 30 SOTA models, and found that it generally performed better than others, so in all domains. Okay, I will skip this part. Okay, and we want to see if we have indeed solved the negative transfer in all domains. So we did it by extracting the performance of each domain from SDSR model, SASREC, and also extracting the performance of each domain on CDSR model, such as CADART, main, C2DSR, and so on. And then directly calculating the difference between two performance. Okay, so as you can see, so most of the CDSR models performed worse than SDSR model, the SASREC, but our model performed better except book domains. Okay, so this suggests that we have effectively solved the negative transfer problem seen in other CDSR models. Okay, so we found the same result in telecommunication company dataset. Okay, I'll skip this result. And lastly, this model is currently being applied in various recommendation systems in our personal assistant app. So our model's practical deployment in SK Telecom's recommendation system led to 21% increase in click-through click-through rate compared to existing ML models. So we believe that our models offers variable contribution to field of recommendation systems in real-world applications using multiple domains. Okay, thank you for your attention. So please feel free to ask any questions. Yeah.